My name is Dr. Norbert Linke. I'm a new assistant professor here at Duke and I'm part of the DQC, and I work with trapped atomic ions in quantum technology applications. I was a postdoc with Chris Monroe at Maryland, and in my lab we kind of established the first programmable ion trap quantum computer, and from there we built it out as in a kind of user facility style, where we operate this not just as a physics experiment but also as a kind of computing facility where external collaborators from national labs, companies, other universities come to us with quantum algorithms and other applications, quantum simulations and so on. And we will collaboratively then realize these applications on our trapped ion system. And then I became an assistant professor at Maryland, kind of moving this idea along. And when Chris got the opportunity to build this new quantum center here at Duke, I was given the opportunity to join, and I jumped on it, of course, because I think we can kind of really expand this idea of a quantum user facility on a larger scale with multiple systems and so on. So then the DQC has a kind of control room that allows you to operate systems remotely, and that really tells you that we're no longer dealing with an atomic physics experiment but actually with a programmable system that can be operated from an interface, and you don't have to actually twiddle any knobs in the lab continuously, but you can actually run different applications remotely via an interface. And so that will also allow external users to collaborate with researchers here at DQC to realize new quantum technology applications. So this lab space has to fulfill a few requirements. So these are optics experiments, which means we need good vibration stability, good temperature and humidity control, and we need to control the magnetic fields, because these trapped ions, they are sensitive to the environment magnetic field, and if that fluctuates, that can cause decoherence to these quantum computations that we are running. When choosing a layout for these tables, I try to make a compromise between table space, as in surface area where you can install optical experiments, also rack space, because a lot of these experiments need a lot of electronics to control them. Additionally, a lot of the optical elements that are more standardized, like some of the laser systems, are now rack mounted, so they don't need to go on the table anymore. It's a compromise between table space, rack space and space for researchers to work. Because in this lab I also want to develop new technologies, new traps, new quantum network applications, and so they're not immediately going to be run as a facility like you've seen downstairs, and so there will be a lot of interaction between people in this space too, so I made sure it wasn't too cramped. And so these were the kind of requirements I had to fulfill when laying out this space, in addition to the usual fire safety, egress and so on. So as I mentioned before, the magnetic field is important and we want to control it, so all the tables have non-magnetic top skins. There's one experiment which is particularly sensitive to the magnetic field. I'm going to be using strontium ions, and the two states that I'm interested in are actually linearly dependent on the magnetic field. They are several orders of magnitude more sensitive to the magnetic field than the ytterbium ions we use as qubits in our other experiments, and so it's very important to minimize the amount of magnetic material around the experiment, and that's why I chose to take two of the tables and make them not just top skin non-magnetic, but basically the entire internals of the table are also non-magnetic. But it's important that vibrations are minimized, and for that reason it's important to have damped optical tables. Additionally, we are on the 4th floor of this building, which means there are modes in the building that cause vibration, and we are near a train track. And all of these things kind of combined mean that good vibration control is essential when building up this lab. There will be two kinds of experiments in this space. Kind of in the back half over here will be the strontium quantum network experiment. I'm kind of researching a new way to interface quantum computers using entangled photons, and strontium ions can produce a wavelength that can be sent through optical fiber over several kilometers without frequency conversion, so it could form a technology to build, I would say, a city-size local area quantum network. And then the front part here will be a quantum computing lab where we're going to use ytterbium ions to realize quantum algorithms in this user facility style that I introduced earlier. And in particular, we're working on a new ion trap technology that's based on fused silica. So the idea is to take basically a slab of glass and remove everything that's not this kind of ion trap shape that you saw downstairs. So it'll be a kind of monolithic ion trap that's made out of one piece and very precision fabricated, and we'll kind of test and use that in this half of the laboratory. The experience with Newport was actually very seamless. They are kind of an established partner of the DQC from the downstairs labs, so they kind of know what the requirements were. They were very quick to respond to my inquiries. I got quotes and the interaction was very positive, I would say. Everything was delivered on time, and so I'm happy with how things went.